And so those are two chapters actually in our textbook. The first chapter 12 is fundamental of radiation. He's trying to explain to us what is radiation, but the problems really, the problem that will show up in the quizzes and the exam are in chapter 13, right? So chapter 12 really introduced just the concepts, right? So this is chapter 12. So you know that chapter would look really complicated, but it's not. Okay. Eventually, you know, how did we when we have convection or conduction, say from a pipe to an outside flow, whether that flow is by external convection, natural convection, the whole problem eventually become, here is Tn and here is T out, and then there is bunch of resistance that we will calculate them, right? And then eventually that Q would be Ti minus T infinity over all those R convection plus R conduction plus R convection, and if there is insulation we plug it in. Well, the same thing will happen in this radiation. So we will also have nodes that represent those bodies, say that the wall and you are sitting in the class and the wall is radiating and you're trying to figure out how much radiation is coming from that wall, how much watt per meter square, or how much watts eventually that will hit you. And so we will also represent the resistance of the ambient to radiation and your close or your surface resistant to radiation as resistance. And that node, it's not temperature, it's something called the radiosity of the body. It's basically its state that represents whether he will be willing to radiate that much or not, right? And so eventually we will say that Q dot is going to be that J1 minus J2 over the R. So we will spend today basically figuring out how we can calculate those resistance. What is the surface resistance to radiation? I bet you realize that some surfaces are more radiating than others, right? That's why we tend to wear black in the winter and we tend to wear white in the summer, or light color in the summer, right? Because certain surfaces radiate that much more than others. So we will figure how we calculate those resistance, right? And we will understand what is this radiosity. But that's how we are solving our problems, right? And in the final last year, that was the problem was basically two walls, and those two walls separated by 5 aluminum plates, right? So actually, even in the final, I drew 4, but I told them in the problem there are 5 shields. So they were confused. But of course, you stick to the problem statement. The problem said 5 shields. Okay, so 5 shields, right? So, and say this wall is sitting at 300 Kelvin, while this wall is sitting at, say, 1000 Kelvin. And he's trying to figure out how much radiation will end up going from one wall to the other. All right? So those are the kind of problems that we'll solve. How much is the Q? It's that J minus that J over the R. So let's figure out now what is the J and what's the R and all those things. So first, radiation is different from conduction and convection. From what point of view?
No contact required.
Right, no contact, no medium even required, right? So eventually, initially when they were trying in the early 1800, when they were trying to understand what is heat transfer, they thought that heat transfer is this, you have this magic fluid inside you, it's called Cyrillic fluid, and the higher your temperature are, the higher the temperature is, the more you got of that fluid. And when we touch another surface, the fluid flow, and that's why the hot lose its energy to the other. Of course, that theory broke down when they realized that, well, how about radiation? Well, the sun is giving us all this energy without any fluid between them, any medium. There is no contact, there is no touching, right? So the radiation does not require any medium. All it requires is that you see that hot surface. If you see it, if there is visual contact, he will come and hit you. Radiation. So all you need is something called view factor. The view factor is that basically how much you see this surface. All right. So if there is a flame outside this classroom, and I am here, I will not get radiation from that flame. I need to be able to see the flame to get radiation out of it. Probably the air will get hot, and then the hot air will go up and go down, and that circulation will end up heating the room. But radiation-wise, you will have to see it, just like in this cartoon, right? If you are in a camping site and you want to get warm, all you have to do is just put your finger or your hand in front of the flame, and you will feel the heat. You don't have to put it on top of the flame to get the hot air, right? If you have a fire, all you have to do is just basically put your hand nearby, right? So even in vacuum, you will get that radiation. So radiation is some kind of electromagnetic waves, right? And those waves have a wavelength and frequency, and the relation between the wavelengths and the frequency is over here in front of you. So the wavelength lambda is the speed of that wave divided by the frequency, right? And we know the speed of light is, radiation coming from the sun is moving at 300,000 kilometers per second. So put another 3 zeros if you would like it in meter per second. And that's how quick it takes. All right? So the light actually, or the radiation coming from the sun, can be expressed as waves, but also you can think about it as particles, photons. And each one of those photons actually have an energy. All right? And this will be important later on when you take courses like energy conversion, when they start talking about solar photovoltaic panels. When you take this energy and convert it immediately into electrons, you would need to understand this part. All right? But for us right now, what's important to realize is that the wavelengths of the solar radiation is not one wavelength. The sun sends a bunch of waves. The radiation coming from the sun come on a spectrum, not just one, right? So the wavelengths that we actually see is just very narrow. It's the visible wave range, right? And that's from the violet all the way to the red. But there is infrared and ultraviolet range that we don't really see, all right? And any surface that's above 0 Kelvin, which is basically everything in this room, radiates, right? It's just that the radiation is not in a wavelength that you see, right? They don't radiate in the visible wave range. They radiate, and that's why if I turn off the light in this room, if I can manage to turn it off, I can't. But if I turn off the light, you will all disappear. I will not see any of you, right? But if I put an infrared goggle in the dark room, I will start to see all of you in infrared. Some of you are more hotter than the other, and there will be more brighter. But I will end up seeing you. Why? Because you are radiating in infrared. The sun, it's not just radiating infrared, the sun is also radiating in the visible range, which are those colors. That's why we see the sun radiation. So if we look here, this is the sun radiation as function. So this is watt per meter square micrometer. So he's splitting the watt per meter square as basically function of wavelengths. So you can see at different wavelengths, what do we see, or what radiation we get. So the sun is basically this over here, and the dotted, it's the black line that, or the dark line that's here, that's solar radiation. And you can see on top of it, that dashed line, that's a black body radiation at 5,760. So a black body is basically the perfect emitter. It's, if you put any body at this temperature, nothing radiates more than the black body. And we are basically, we are not black body, we are gray body. So we are not radiating as strongly as this. So there is a ratio between your radiation to a black body radiation. So Jason, for example, right now he's at like what, 90, what's your?
Hopefully 98.
98, right? 98.6 hopefully. So if you bring a black body at the same radiation as Jason at 98, we will get more radiation from that black body than from Jason. So Jason will radiating a fraction of that black body. So that fraction is epsilon. It's the emissivity of Jason, right? So you will have an emissivity of 0.7, for example, or 0.5, right? So you can see the sun is almost like a black body at that temperature, all right? So that radiation arriving to us at the outer atmosphere is almost 1300, right? 1300 watt per meter square. So this International Space Station outside the Earth's atmosphere get every meter square of its wings gets 1300 watt per meter square. And those solar panels on the International Space Station convert those energy with a certain efficiency to electricity that power the International Space Station, right? And the same apply for all those satellites. You know, they have those solar wings or solar photovoltaic panels, and they convert that energy to electrons. However, we don't get that radiation. On the Earth here in Tulsa, Earth's surface, we get slightly lower because of the scattering of the atmosphere. Our atmosphere reflects bunch of wavelengths, absorb bunch of wavelengths. At the end of the day, we get only this much, right? And you can see the ozone is basically killing a lot of them. The O2, H2O, all those gases in our atmosphere absorb and scatter and reflect, right? At the end of the day, what we get from the sun really peaks at, look at this, it peaks at the visible wavelengths. So, which is what our eye can see. So it's either the sun was created for our eyes or our eyes developed for the sun. But either way, we are a perfect match, we and the sun, right? So the sun gave most of its radiation where we can really see it, right? So good, we are lucky, right? But however, there is a long tail, and that's the infrared radiation. So those are all joules that's coming every second, right? And again, depending on the temperature of the body, the peak will shift toward that short wavelengths. So 100 Kelvin surface would radiate mainly in the infrared, and the hotter it gets, the more the wavelengths will shift, the peak will shift toward the visible wave range. That's why if you end up working in a steel furnace, and they sometimes they'd like to figure out how hot is the furnace to cast, iron, or so they can tell not by putting a thermometer but by just looking at it. And they have a color chart on the window, and they basically move the color chart until the flame disappear from them, and so that's the perfect match. And then they say, wow, see, it's basically the temperature right now is 1200 Kelvin, because just the flame basically disappear from them when they try to match it with this orange reddish something, or like it's even brighter, it become orange yellowish, and then it become yellowish whitish, and then it's whitish. All right. So you will see all the radiation, right? It's just that the mix will shift more and more toward brighter and brighter, or as you get more and more higher in the temperature scale. Okay? So the point behind the story is that everything above 0 Kelvin radiates. Alright, so if we are trying to calculate how much radiation a laptop in the room will get, you'll have to consider radiation he's getting from the wall, radiation he's getting from the floor, radiation he's getting from the other computers in the room. Alright? It's talking about, those big data banks. It's Google server, for example, and you can see like they really have very hard time cooling all those servers because it's a lot of energy and there are so many of them in the room. Or say the lithium battery in Boeing 787, and how can you keep it cooling without igniting? So those things will have convection, conduction, and radiation, and they will radiate. They don't have to be glowing white to radiate. As long as they are above 0 Kelvin, they will radiate. All right? And so we will try to calculate how much is that radiation. So if we integrate the area under all this curve, not just per every wavelength, but all the radiation, it will end up being sigma T to power 4. So that E, this is per wavelength. I radiate this much in that wavelength, this much in that wavelength, but eventually at the end of the day, how much is radiation coming out from me? It's sigma multiplied by T to power 4. T here is in Kelvin, so always remember that's a big famous mistake. They put it in degree centigrade. No, T should be in Kelvin, and sigma, that's Stefan-Boltzmann constant, right? And that number is, it's the easiest number you could ever remember. 5.67 multiplied by 10 to power yes, 8. Watt per meter square. Sorry, watt per Kelvin to power 4. Watt per meter square Kelvin to power 4. You will see the number in a second. Right? So if we have, say, a flame over here in the middle, right? And by the way, I told you that in space the flames are not pointed up and candle-like like our flames on the surface here. The flames on space is basically a sphere. If you ignite anything, it just make a blue sphere around it, right? Because why would the air, the hot air that's coming from the ignition, go up? He doesn't really want to go up, or right, or left, or he doesn't have any preferred direction. So he just basically diffuse, right? So let's imagine having a sphere like a flame like this in the middle. How much of the radiation leaving that flame will end up going to this wall, or how much will go to the ceiling, or how much will go to the other wall? How could you tell the share of each surface in the room from that watt per meter, or how many watts is generated inside this flame? It must have to do with what do you think? Let's have a flame in the middle of this room, and I'm asking you how much is the ceiling going to get? So Jesse is saying it's probably how closer it is from the flame. So it really has to do with, if we imagine a sphere around that flame, or a sphere around this body, what is the share that this surface occupy on that sphere? Okay, so it's like a kind of, in a 2D, it's a pizza, and you are trying to figure basically what is the share that this arc represents of the whole circle. So we measure the circle in radian, right? We measure the shares in radians on a 2D circle. In 3D, they measure it in solid angle. So what is a solid angle? You should think about it as basically kind of the surface area of that sphere that occupy. So for example, if that flame is sitting between two parallel plates, and those two parallel plates are very, very big, infinitely long, I bet each surface will take how much of the energy leaving? 50%, right? So he occupied half the sphere, or his solid angle will end up being equivalent to half the wall, right? So that's how they come up with this concept of the solid angle. So the solid angle, and the solid angle of the whole sphere is 4 pi. So half the sphere is 2 pi. All right? The next thing that we'd like to discuss is that every surface, when the radiation end up hitting it, the watt per meter square coming from the sun, for example, falling on the roof of your house, some of that will get reflected depending on how shiny the surface is. All right? And so this is rho. It's the reflectivity of the surface. So if the incident radiation G 1000 watt per meter square, and you have reflectivity equal to, so the higher the reflectivity, the more shiny the surface is. So for example, a mirror will have a reflectivity of 1. So mirror would be a perfect reflector. All right? A black roof in your house probably have a reflectivity of something really tiny, not really 0, but you know, because you can eventually see it. So it reflects something. Right? So rho multiplied by G, that's basically how much radiation will end up being reflected. Alpha times G, alpha is absorptivity of the surface. So some surfaces are more absorptive than others, of course. That's why if you look to any solar heater, those are heaters that basically use the sun to heat water. You will find they are painted black because they want them to absorb radiation really, really strongly, right? And that's also why we wear black coats in the winter, because you know we'd like them to absorb all the radiation they can get so that they can make us really feel warm, right? So a white winter coat is really a bad idea. Okay. So alpha is absorptivity, rho is reflectivity, and if this surface is transparent like a glass plate, you will have rho and alpha, but also you'll have tau, and tau is the transmissivity. So eventually at the end of the day, of course, alpha plus rho plus tau equal 1. Right? And I remember one year I had the multiple choice question for them in the final, telling them for an opaque surface, alpha plus rho equal 1, tau equal 1, and other choices. And so the answer was, yeah, for opaque surface, what is an opaque surface? He does not let anything go through. It's not transparent. It's the opposite of transparent. So a big surface is basically something that you cannot see through. The radiation cannot go through. So of course, alpha plus rho would be 1. I mean, he will absorb something and reflect something, but he will not be able to let anything go through. All right? So those properties are function of wavelengths, meaning that some surfaces are transparent to some radiation, some wavelengths, but opaque to the others. All right? So for example, a silicon wafer, a piece of silicon is transparent for infrared radiation. So if I have an infrared camera or infrared goggles on my eye, I'm looking to you through an infrared camera, all right? And it's completely dark, I'll turn off the light, I'll still be able to see you, right? You'll like be red zombies in front of me, in front of the... And if you put a piece of silicon in front of my eye or in front of my infrared camera, I will still be able to see you, because the silicon basically let the infrared radiation go through. It does not block it. All right? So the same thing for glass and the visible range. So the glass will let basically the visible light go through, but it blocks the infrared. So that is a problem, because then, you know, that's why our cars get really, really hot in the summer, because it let all the radiation that's coming from the sun go through, and then the car gets really hot, the seats are very hot, the steering wheel you cannot even touch it, okay, because it's really, really hot. And why all this energy, the car is even hotter now than the ambient, and the trees, and right? And actually in Detroit, one professor left his child in the car and went to give his class, and he forgot that his child was in the car, and the child died. That's a true story. So why did the car get that hot? Because all the radiation inside the car cannot go through, right? Because the car seat and the steering wheel and all those things will never get above 800 Kelvin. They will melt first before they go to 800 Kelvin, right? So as a result, all the radiation leaving them cannot go out, and they get trapped. Fortunately, now there are certain car glass shield that they tell you that it's selective, and the glass basically is allowing it to radiate back somehow. All right? All right, so this is an important phenomenon that's basically can affect also the surface on Earth, right? So you know how greenhouses, we hate this phenomena in our cars, but we love it in greenhouses, so that we can maintain a place in your garden to be extremely hot even in the very cold winter. Why? Because all the radiation comes through and then you wouldn't let them get out. All right? So then you can even raise tropical plants inside them. Well, the Earth's atmosphere also behave the same way. So H2O and CO2, they have the same thing. They could absorb and they wouldn't really let the radiation from us leave back at night. So in the morning, they will let the radiation from the sun go through. We get hot. But then at night, where all this radiation, we are supposed to radiate back to the space. You know, when we turn our back to the sun, and now we have this very cold space, we can get cooled now, right? Well, we can't if there is too much CO2 and H2O. Because, again, look at their transmissivity. Very good for the visible range, where the sun is sending its radiation, but then go to zero when it comes to our radiation. All right? All right, and that's why he's talking about this much. Okay, so now we understand the concept of what is radiation, and it's all those waves coming at certain wavelengths, right? Yes?
How is that proportional to like the amount of CO2 in the atmosphere?
So James' question is, how much would this be affected by the amount of CO2 and H2O in the atmosphere, or how much does it take to really make this significant? I guess that's the question, right? And that's not the right course for that question. So so basically, James is asking about, well, you have like a relation between the particle per million of CO2 and H2O in the atmosphere and the percentage of how much radiation get blocked. I don't have this number on top of my head. But the phenomena is well documented that if you have gases, they call them greenhouse gases. In the atmosphere, they will have this effect. They will let radiation go through, but they wouldn't let lower, just like the glass in your car. You meet exactly.
Does the thickness of the glass change?
Well, of course, if it's like really thin, there's not that many molecules that can block that radiation that much. So yeah, it makes a big difference, right? Yes. All right. So now radiation is actually very important for furnaces. That's how you can heat the whole thing, right? It's very, very important for fire accidents. You know, if you have a fire, the heat will move from one place to the other just by radiation. That's why they tell you keep the doors closed. It's not conduction and convection. But the fact that you see the flame, that make you really hot. You know, John Zink over here, those are a very big company in Tulsa with a huge share market worldwide for making furnaces and burners basically in flares. And they had this huge flare, really big one that they tested, and it make huge flame to the extent that when they basically, before they turn it on, they have to tell the airport that we are going to turn our flame. And so that flame, actually, you can burn or you can get very, very hot at least if you get close to it. You don't have to touch it. So just standing far away from it, you can feel the heat of the thing. All right? So there's a lot of, and all of our radiation basically coming from this, all our energy coming from the sun by radiation. So that's a very important mechanism to understand. All right? So in order to make our problem easier, we will assume that all our bodies basically radiate uniformly everywhere. That's not really true. In some surfaces will radiate more in one direction than others. All right? And we also assume, so we assume basically perfect uniform radiation. But in real life, it will be like this. All right? And also when radiation fell, it could reflect perfectly. That's specular reflection. That's like a mirror. all right? And that's the kind of radiation that you would like to have in solar thermal power plant. You know what's a solar thermal power plant?
Field of solar panels.
Right, a field of solar mirror, and those, if I can get my browser. Forever, but it's basically there are all those mirrors on the floor that's radiating all or reflecting all the radiation to one central point where they basically put a furnace here. All those mirrors are sending all the radiation to one single point. Of course, you put your anything here and it will basically burn. Right? But here there is actually a furnace where there's water pipes, and those water pipes basically make the water boil, and you can make steam, and then that steam basically can use it for turning a turbine. Here's another picture. All right? So for something like this, you would like to have the perfect mirror for it. And so they always keep it clean, of course. They have robots for it. And then there is the diffuse radiation. And so we will assume we have diffuse radiation like this. When you receive the radiation, the body kind of absorb that radiation and then emit it back everywhere. All right? So the real life, of course, is not this and it's not that. It's usually something like this. So yes, the majority of the radiation will come and will go. The majority will go in that direction, but it's not like a perfect mirror. It will radiate in that direction. So the surfaces over here will get more radiation than surfaces like this. But we will ignore this in our problem to make our solution easier on us. All right? So this is what we are going to assume. Right. And so the whole. So again, what is our job? We are trying to calculate those resistant radiation so that we can say that the Q is J minus J over those resistance, right? And so the resistance of the space to radiation, whether I will be able to get radiation from that flame outside the classroom or not, it depends on how much I see that flame, all right? Or basically, how much does this flame see? He sees the corridor and he sees the ceiling and he sees the floor, and I represent only 10% of his view. So I probably will get only 10% of his radiation because I only occupy 10% of his sky. If you imagine there's a sky on top of that flame, I am only 10% of it. So I will get only 10% of his radiation. So to calculate this number, we have to depend on something called the view factor. All right? So the view factor or the shape factor or the angle factor, it's really how much you occupy of the sky of that surface you are trying to calculate the radiation from. And we'll give it the symbol F. All right? So Fig represent the fraction of the radiation leaving I and come to J. So F flame Dr. Salam will represent how much of the energy or the watts leaving the flame and coming and hitting me. All right? Well, does F flame Dr. Salam is the same as F Dr. Salam flame? If I'm getting 10% of the flame, will that mean that he will also get 10% of my radiation? No, not necessary, right? There's a relation between them actually. They are not the same. There is a relation between them, and that relation, we will prove it. Let me jump to it. So he will prove it here. So he is trying to develop how much is the Q leaving the surface I going to J, and how much of the Q leaving surface J come to surface I. And so I will let you actually read this derivation. I don't want to read it for you. But it turned out, so here is F12. So this is the fraction of the Q leaving 1 and hitting 2. And here is F21, the fraction of the radiation leaving 2 and hitting 1. And the relation between them is this. And this relation is really very important for solving all problems actually. And so that it's called reciprocatory fraction or reciprocatory relation, because it tells you that A1 F12 is the same as A2 F21. So the ratio between the F flame Dr. Salam to F Dr. Salam flame is basically our surface area. Alright? So area flame F flame Dr. Salam is the same as area Dr. Salam F Dr. Salam flame. Alright? So of course if our area is the same, then we get the same fraction. Something like this. You know, they are basically looking to each other. I bet F12 will be the same as F21 when we prove this. But if it's something like this and something like this, you can guess right now that probably F12 is not the same as F21. Right? The big surface will probably get all the radiation leaving that surface. Right? Most of it. But that small surface will not get all the radiation leaving the big surface, right? Because he will radiate like this. Okay. So the proof again is on this 3 pages, and it's all geometry, and he basically just trying to figure out how much Q is leaving 1 and going to 2, and how much Q is leaving 2 and going to 1. All right? So now, so this radiosity business, what is this? What will decide how much radiation leave the surface? And it's not the temperature, it's called the radiosity, J. And what is J? So the radiation coming to hit you, falling on you, is G. Alright? So G is how much radiation is coming, falling on you because of the other surfaces around you. Okay? So some of that G will get reflected. How much will be reflected? If G is, say, 1000 watt per meter square, how much will be reflected? Anyone? Rho G, right? And you will have your own radiation, because we said anything above 0 Kelvin will radiate. How much will you radiate? Sigma T to power 4. That's if you are a black body. And if you are not a black body, which we are not, then it will be epsilon multiplied by sigma to T to power 4. This plus this. This is the total of what will leave you. And this is how you communicate to the outside world. You communicate with your J, your radiosity. And it's basically those two guys together. Alright? So now this, depending on how hot you are, say 1200 watt per meter square. Those 1200 watt per meter square will end up going to the outside world. Alright? And they will get split. Maybe 500 will hit the students here standing in front of me in the first row, and maybe 200 will go to the people at the back because they are a little further away. 100 will go to the ceiling, 100 will go to the right, and probably very little will go to to the outside, because I can hardly see the outside. I only see part of the outside from that creek and from that space in the between the door and the frame. So the radiosity gets split, all right? And that will determine basically how much Q will go from me to the room ceiling and Q leaving from me to the floor, all right? So it's the G. All right. So now the whole chapter is filled with tables for that F. Just like in natural convection and forced convection, we have tables for different Nusselt number of a cylinder, Nusselt number for a flat plate, Nusselt number for, and so on and so forth. Over here, we will have tables for view factor, because that F is really the resistance. We will see how much is the resistance, but the resistance is based on that F. If you can see him, you probably will radiate very well to him. If you don't see him that well, because he's hiding, because the angle is really far away, you will not radiate to him that much. There will be huge resistance. All right? So the chapter is filled with tables and equations and charts to calculate those F for different geometry. 2 barrel plate, 2 perpendicular plate, cylinder and a bigger cylinder, 2 spheres on top of each other, stuff like this, all right? However, the difficulty here in this chapter is that the table and the chart don't cover all scenarios, and we have to fill in the gap, all right? So how we are going to fill in the gap? By those, there are 4 rules that we are going to use. The first one of them is this. So if you can find a table that will give you F1, 2, again, this big body to a small body. Here is 1 and here is 2. But there is no table that gives you how much is F21, how much radiation is leaving the small guy and going to the big guy. How do you do it then if there is no table or equation for it? You do it from here. You do it by saying, well, I can get F12 from the table, but then I will use A1 F12 equal to A2 F21 to get this F21. All right? So that is the first rule.